So what I want to do in this lecture is briefly talk about efficiency and losses in efficiency of DC machine. So this is the topic, and if time permits, we will also talk about armature reaction of a DC machine. So for the time being, we'll just go with this topic. So before I move forward, let me show you what we did in the last class. So I understand that there is some kind of a online platform for sharing the class notes and all, which is called. Listen to me. Sorry for the interruption again. So let's continue what we had done in the last lecture. So in the previous lecture, I recollect, towards the end of the lecture, I was asking some kind of homework. So let me begin by asking whether anybody has done this homework. So this was the lecture 6, and in lecture 6, just towards the end, we wanted to plot the load current from 0 to 200 amperes and the efficiency, how the efficiency changes with the load current. So this was homework. So did anybody do this? That's my first question. Hello. Done. So today's class, let's begin by looking at this problem. What was it? So if I just review, so this was the question that was given, example number 13, and the given data. So you can see on your screen, this is the given data. That is 45 kilowatt is the capacity of the machine. That is the output of the machine will be 45 kilowatt. That is the DC shunt generator rated output, and 230 volts is the rated terminal voltage, and it is a DC shunt generator, and the full load efficiency is 90%. This is given, and friction, iron, windage losses are 1000 watts. So, and the shunt field resistance is 70 ohms, and armature resistance was asked. So as a process of solving this problem in the last class, we had created this diagram. So this is a diagram of DC shunt machine. So you know, like this is the armature, this is the armature resistance, this is the field winding and field resistance, and then 45 kilowatt is the output voltage, so output power, and the voltage is 230 volts. So how did we solve this problem? So first we made this calculation, find the load current. So the output power divided by voltage will give me the load current. Then find the shunt current. So shunt current will be 3.28. This will be constant, assuming that we are maintaining the shunt voltage as constant all the time. That is the voltage 230 volts constant all the time. Then accordingly the armature current will be the addition of these two. So I got the armature current, and from that we went to the power diagram. Then the output power was 45, and the input power we can calculate from the efficiency. Then from the input power, if I remove the 1000 watts of losses, then I get the power developed, that is 49000 watts. And from that power developed, if I look at the difference loss, and from that copper loss I can find out the uh, actual copper loss in the armature. So we had done all these things in the lecture 6. So if you refer to your notes, these things we have already done. So I can find out the generated EMF, I can find out the IARA drop and all these things. So finally the resistance I got is 0.82. So this was the one part of the problem. And the remaining part of the problem was the homework, that is calculate the efficiency versus the load current plot when the voltage is maintained at 230 volts. So shall we try to do that now? So to try to do that now, so let me recreate the problem. So let's call it example 14. All right. So I'll just simply repeat the given data. So it's a DC shunt generator, and I have armature resistance 0.08. That's what we calculated. And the shunt resistance is 70 ohms. Terminal voltage is 230 volts. This is maintained. Maintained at 230 volts for all loads. Okay, so what else is given? So the given data, that is the friction and windage losses. And iron losses. This is 1000 watts and this is also constant. So now the question is plot efficiency versus the load current. So if the load current is varying from 0 to 200, how the efficiency is varying? So this is the question once again. So I'll just give you 2 minutes to think about this question, how to solve this question. So just I'll take 2 minutes time. So just try to think about how to solve this question. It is very important to understand this, and once you understand this, you got good grip over the DC shunt generator, how the efficiency varies with the load current. So just think about how to solve this. So the clue is you can try to draw the draw the circuit diagram and the power diagram. So just take 2 minutes. If you want to know efficiency, so we begin by writing the formula for efficiency. So of course, to make a plot, we have to use a software program, but anyway, let me just do the initial mathematics. So what is efficiency? Efficiency is output divided by input, or this is nothing but output divided by output plus losses. So what are the losses we have in a DC machine? So first of all, how do we get the output? So nothing but voltage into current. So whatever is the output voltage and output current, that is nothing but the, because it's a generator, generator output is electrical power is nothing but voltage into current. So similarly, the output is again voltage into current plus losses. So what are the losses? Losses are friction losses, so friction and iron losses plus copper losses. So what are the copper losses? Copper losses are shunt current square multiplied by shunt resistance plus armature current square multiplied by armature resistance. So this is the copper losses. So everything we have covered. So if I want to know efficiency, I have all these things. Now further details, you see voltage is 230 volts, that is fixed given in the question, multiplied by current, current keeps on varying. Similarly, voltage is again 230 volts multiplied by current plus. What is the friction and iron losses? That is given, that is constant, that is 1000 watts, that is given in the question, because friction and iron losses are related to flux. Flux is maintained constant, and the rotation also more or less not changing. So mechanical losses, everything will be constant. So this is fixed. Plus, now what is the shunt field current? So shunt field current is also constant because voltage is maintained constant, and then the resistance of the shunt field is also constant. So let me calculate that. So what is ISH? ISH is nothing but V by RSH. So that is nothing but 230 volts divided by 70 ohms. So that is nothing but, we had done that calculation before. So let me once again quickly do that calculation. So 230 divided by 70. So 3.28 amperes. So this current is fixed. So what is the shunt losses? So ISH square RSH is the copper loss in the shunt field winding. 3.28 square multiplied by 70. So let us see how much it comes to. So 3.28 square multiplied by 70. So I'm getting 753 watts. So this is also constant. So if I go down, so here in the place of I square RSH, I'll write 753 watts. Current is nothing but shunt field current plus load current. And then armature resistance is 0.08. That is given in the question. So here shunt current also I know. So therefore I just have to find out the value for I, and then I'll get the efficiency. So finally, once again, if I see efficiency is equal to divided by 230I plus, now what is the addition of these two things? 1753. So I hope you are able to follow what I am explaining. Now here I can write ISH is 3.28 plus I whole square multiplied by 0.08. So this is the efficiency. Now if I substitute the value of I can find the value of efficiency. So it is now the simple thing of plotting it. So for generating a plot for this, let us use a MATLAB interface. So let me open that. Just give me a minute. Meanwhile, you can just Meanwhile, I'll open. So now given this formula, so I'll share the Octave screen with you. So let us try to implement that. So on your screen, you are able to see the online interface, that is Octave Online. It is nothing but same syntax as that of MATLAB program. So let us write a small program for this. So let me begin by defining the current. So I have first line number 1, clearing the screen and clearing all. So next line number 3, I am just defining current is 10 amperes. So I have defined the value of I as 10 amperes. Now what is the efficiency? So EFF equal to, so already we worked out the formula. So 230 into I divided by plus 1753 plus, I'll once again open the brackets, 3.28 plus again I, this to the power of 2 multiplied by 0.08. So like this, I am defining the value of efficiency. So this is just a simple calculation of efficiency. So now if I save this program, just only 2 lines program, if I execute this program, here can you see the efficiency? On the right side, the result is coming 0.5655. That means what is the efficiency? 56%. So when the current is 10 amperes, the efficiency is 56%. So I'll increase the current. So if I change the current to 20 amperes, okay, now if I save and again run the program, so on the right side, you see the efficiency increase to 71.916%. So like this, just by changing the value of current, I'm getting the efficiency. Now instead of getting a single value every time, I want to get different values. So in MATLAB, you can define something like this. So I can say starting with, so by the way, what happens if I give 0? If current is 0, then what will be the efficiency? So you can see on the right side, I equal to 0, efficiency is also 0, because if current is 0, output is 0, and if output is 0, then efficiency is output by input. So 0 by anything, it will be 0 only. Okay, so now I'll define 0 colon 10 colon 20, 200. So now look at the line number 3. So I'm defining I equal to 0 colon 10 colon 200. So this will create a series of values for the current. So that is in the steps of 10. So that means 0, 10, 20, 30, 40, 50 and so on up to 200. Like that it will create the series of values. So let me just comment the efficiency. I'll run this and show you. So you can see on the right side, the value of I is shown like this, 0, 10, 20 and all. So here you can see on the right side, the I value 0, 10, 20. So instead of single value, I am taking multiple values of current. And for all of these, I can calculate the efficiency. So for that, I just have to use a dot notation. So here I have to use dot. Okay, so now hopefully it should not create any error. So let's run and see. So now on the right side, so again you can see different values of efficiency are displayed. So efficiency starting at 0%, then 56%, then 71%, then 78.9. Like that, gradually you see the efficiency is increasing. So let's make a plot of it. So how to make a plot? So plot so I comma efficiency. The plot has been created. So efficiency is 0 and increasing, and then it is kind of maintaining. So this is the kind of plot we are expecting. So let me improve the plot. So how to improve the plot? So I'll just give star and dash, and then I'm defining the higher line width. So here you can see how the efficiency is changing. So the x-axis is the load current and y-axis is the efficiency. So is that clear? So any doubts about this? Just take a couple of minutes. So the everything is there also there. Just see, and if you have any doubts, feel free to ask. I'll just give you a couple of minutes time. Okay, so the question is like this. Given so it is a short shunt compound DC generator, and now we have this data. So from this, what is the drop in the series winding? Drop in series winding. So that is nothing but ISE RSE. So the current already is given 100, and then the RSE is 0.025. So that is nothing but 2.5 volts. So therefore, armature voltage VA will be nothing but V plus VSC, voltage in the series winding. So that is nothing but 2.5 plus 200 volts. I'm sorry, this is 220 volts. So here I can give 220. 2.5 volts. So this is the voltage of this point, 222.5 volts. So then I can now find out the shunt current. So what is the shunt current? Is nothing but armature voltage divided by RSH. So that is nothing but 222.5 divided by shunt current is like resistance is 50. So that is how much? So 222 divided by 50. So this current comes out to be 4.45 amperes. Now that I calculated the shunt current, so therefore from this I can find out the armature current. So this is 4.45. So therefore the armature current will be the addition of the previous two currents. So this is 4.45 and this is 100. So I will get 104.45 amperes. So IA is ISH plus ISE. So that is this is because of it's a short shunt machine. So that is nothing but 104.45 amperes. So therefore drop in the resistance, drop in armature is nothing but 104.45 multiplied by 0.05. So how much will that be? So this is 5.22 volts. So then this voltage drop, so therefore what is the generated EMF? EG will be nothing but brush drop, that is 2 volts is brush drop. 2 plus 5.22 volts is the armature drop plus the armature voltage here, that is 222.5 volts. Two plus 5.22 plus 222.5. So total I am getting 229.72 volts. So this is the EMF generated by the machine. So therefore, now if I draw the power diagram, so what is the power diagram? So power diagram, I am getting something like this. So the output power P out is nothing but V into I. So I have 220 volts multiplied by 100 amperes. So that is nothing but 22,000 watts. This is the output power. This I know. Now what is the PD, power developed? So nothing but EG multiplied by IA. So power developed will be product of the EMF generated multiplied by current. So that is nothing but 222.72 multiplied by, what is IA? IA we had calculated here 104.45. That is 104.45. So let me do this calculation. So I am getting 23,994 watts. So this is the power developed. Therefore, the difference between these two will be nothing but copper losses. What is the copper loss? Just the difference between these two. I am getting 1994 watts. Now, similarly, the iron and friction and iron losses. This is already given in the question. So if I go and refer to the question, so that value already given is 1 kilowatt. So I go back and then I'll write here 1 kilowatt. And if I write 1 kilowatt here, then finally if I add 1 kilowatt, this will be 24994 watts as my power input, or the power delivered by the prime mover. So input power is this much, out of that 1 kilowatt is lost, power developed is this much, out of that 1994 watts is lost, and finally the output is this one. So therefore, if you want to find the efficiency is nothing but output power divided by input power. So that will be nothing but 22,000 divided by 24,994 watts. So that is nothing but so we are getting 0.88, or this is nothing but 88%. So this is the overall answer for the question. So any doubts about this question? I hope you are able to see my screen. Yes, so I got a reply from DMS SVHCC. So 229072 and then 0.88. So good. So you're confirming the answer. All right. So let's do one quick derivation, that is so condition for maximum efficiency. So we know, just consider the shunt machine. Efficiency is nothing but output by input. So we have already seen this before. So this is nothing but output by output plus losses. This is nothing but V into I divided by V into I. Now what are the losses? One loss is WC, that is constant loss, constant power loss, that is friction and iron loss and everything, plus another loss is IA square RA. Now what about shunt field loss? That also is considered inside the WC itself. The shunt power losses also is into this. So now, because the armature current is almost equal to the load current, because shunt current will be percentage wise less, IA almost equal to I. So therefore, I'll get efficiency is nothing but VI divided by VI plus WC plus I square RA. So here I replaced, this is an assumption, IA and I. So now divide numerator and denominator by VI. I'll get 1 by 1 plus WC by VI plus IRA by V. So I'm getting something like this. Now for efficiency to be maximum, denominator should be minimum. So because in the numerator only 1 is there, so therefore if I want to increase the efficiency, I have to decrease the denominator. So here also there is 1. So this part I have to minimize. So at the minimum value of this, the differentiation will be equal to 0. Therefore, d by di, differentiate with respect to the current, then Wc by Vi plus IRA by V has to be 0. So if you just further do one step, differentiate with respect to I. So I'll get minus Wc by Vi square plus here Ra by V equal to 0. So this implies that R by V equal to constant loss by V into I square. So here V can be cancelled. So this implies that I square R should be equal to Wc. So this is nothing but constant variable loss must be equal to constant loss. This is condition for maximum efficiency. So this is condition for maximum efficiency. So any doubts up to here? So for maximum efficiency, what is the current? Wc by Ra square root. So from this, if I just find what is I, then I'm getting like this. So let me give you a question based on this. Let's call it example 16. A DC shunt generator has constant losses of 3000 watts and armature resistance of 0.05 ohms. Determine the load current for maximum efficiency. So I'll just leave it to you. Just try it and try to find what is the maximum efficiency. So that comes out to be, let me just verify that. So 3000 divided by 0.05, 60,000. Then what is the square root of 60,000? Yeah, 244.9 amperes. Okay, So now we have about 10 minutes time. So maybe in this brief 10 minutes time, I'll just start some kind of new topic, and we will continue the topic in the next lecture. So let me create a new screen. That is working principle of a DC motor. How exactly a DC motor works. So again, just go back to the construction. The same machine can be used as a motor and a generator. So you have, so let's say this is North Pole and this is South Pole. So how are these poles created? So poles created because there is a winding here, there is another winding here, and these two windings are connected. So this is the field winding. So what you do with the field winding? Simply you connect it to a voltage source, DC voltage source. So the moment you close the switch, field current will flow and a magnetic field is created. Now inside there is an armature. And there are armature conductors. And these conductors are connected to a brush. So this is, so not exactly, it will be like this. And at the same time, I am also giving the electrical input. So here, this is A and this is A. This is electrical input. So when the electrical input is given, then the current carrying conductor is placed in a magnetic field. So a current carrying conductor placed in a magnetic field experiences a force, and that force will start rotating the motor. So there is some force. So let's say the force is downwards here and the force is upwards here. So like this, some force is generated, and because of that, so here I have a mechanical load. So this mechanical load also will start rotating like this. So now if I increase the load, then it will slow down the conductors, and the moment the conductors are slowed down, more current will come, and again more torque will be generated, and again the motor will start running. So if I want to further look at the details, so just look at the force direction. So there is a magnetic field here, and because of the direction of the current, on one side the current will be dot, and the other side the current will be cross. So it will be like that. So what you can see is, so let's say this is the North Pole, and this is the magnetic field of the North Pole. So all these lines are moving towards right side, and there is a conductor here, and there is a dot notation. So what is the magnetic field of that conductor? If it is a dot, then it is clockwise direction. The force has to be downwards. So the magnetic field will be clockwise direction like this. Now if you look at the top of the conductor, the magnetic field is adding. Bottom of the conductor, the magnetic fields are cancelling each other. So as a result, what happens? Resultant. As a result, we get like this. So the conductor will be, the more magnetic field will be concentrated above the conductor. So therefore, a force is generated downwards. So similarly, so this is a north pole. So there is a downward force on this side. On the other side, the current will be reversed, and the field is same. So there will be upward force. So overall, one downward force and one upward force will result in a torque, and the machine will start rotating. So the another thing also happens when the machine starts rotating. It is cutting the magnetic field, and EMF is generated in that. So that EMF is called back EMF. The moment the motor starts rotating, back EMF is generated. This voltage is the supply voltage V, and this voltage is the back EMF EB. And the formula for back EMF is also same as the EMF generated. So what is back EMF? Back EMF is again flux into N into Z into P by A into 60. The exact same formula is applicable, and this back EMF is opposing the overall EMF, and therefore it is helping in the development of the work. So this is the working principle of a DC motor. So I think we are almost coming to the end of the time. So if you have any doubts, feel free to ask the doubts. Otherwise, we will continue this topic in the next lecture. So any doubts?